This lecture examines the case of estimation and hypothesis testing involving two population proportions. We want to be able to calculate a confidence interval for the difference between two population proportions, but we also want to be able to test whether or not there's a difference between two population proportions. Now, when does this situation actually occur? It is possible that we could have two populations, each of which have a particular attribute that we're interested in, and a certain percentage of the population has that attribute. So, for example, if we were to look at the percentage of investors in Ontario that invest in GICs, right, which are fairly safe investments, and there is a percentage of investors in the Maritimes that also invest in GICs. Question is, are they investing at the same rate? In other words, do we have the same proportion of investors in Ontario and the Maritimes? I got to do this right. And the Maritimes investing in GICs, government investment certificates. All right. So we want to know if there's a difference between those two. We could calculate a confidence interval for that difference, or we could certainly calculate or conduct a z-test for the difference between the population proportions. Before we can go forward with our models, we need to make some assumptions. One assumption that we need to make is that for each population, or for each sample from the respective populations, the conditions that allow the binomial to be approximated by a normal distribution should exist. And that condition is that in the case of sample 1, n1 times the sample proportion should be greater than or equal to 5, and 1 times 1 minus the sample proportion should also be greater than or equal to 5. And then 2 times the sample proportion should be greater than or equal to 5, and 2 times 1 minus the sample proportion for the second sample should also be greater than or equal to 5. So if we have those conditions met, we can go ahead and use a normal approximation to the binomial, which then allows us to say that the sampling distribution of the difference between sample proportions is a normal distribution. Now, we're going to use for our population parameters pi 1 and pi 2. The book notes uses P1 and P2, but so far in the course we've been referring to population proportion as pi, and that's our sample statistic P bar 1 minus P bar 2. So if we want an interval estimate for the difference between population proportions, then the same generic model applies. Our point estimate, which is right here. So the point estimate is a sample statistic, P bar 1 minus P bar 2. So we take these two samples from those respective populations and we take the difference between the sample proportions. That gives us our sample statistic. Our critical value, since our sampling distribution is a normal distribution, will be Z. And then we have the standard error of the difference between the sample proportions is given by this term right here. That's the standard error. Now, what it is basically an expansion of this formula right here in the case of a single sample where we had P bar 1 minus P bar over N. Well, now we have two samples, and so we need to include the second one. All right? So the index 1 and 2 refers to the respective samples. So P bar 1 would be the sample proportion from population 1, and P bar 2, the sample proportion from population 2. And Z, of course, we know is the critical value. So that is fairly straightforward. Notice all of the confidence interval formulas have the same basic form of sample statistic plus or minus the critical value times the standard error. And that's what we have in this case right here. Let's take a look at the case of hypothesis testing. Now, with the difference between two population proportions, we have two cases. I'm going to start off with case 1 and then get into case 2. In case 1, what we have is the special condition where in our null hypothesis, we will assume that there's no difference between the population proportions. But in our alternate hypothesis, we could assume that one proportion is greater than the other, or that they're just simply different. And in that case, we have a special version of our model, which is right here. This is our test statistic. But what you will notice in that test statistic is that we have a value P bar. And I'm going to explain that to you very shortly, why we need this particular value. To calculate P bar, we call it the pool estimator for the overall proportion. And that pool estimator is given here by this formula. Okay? So notice that the pool estimator, or the pool sample estimator, is really combining two samples. That's essentially what it's doing. It's taking all the observations from sample 1 and adding it to the observations from sample 2, and then dividing it by the sum of those two samples. In other words, we create a big sample. To give you an example, let's say we had two populations that we're looking at, two different parts of the province, and we wanted to determine what percentage of students prefer a particular beverage, like a particular beverage. Let's say Coke. So if we took a random sample of 100 in Halifax and 100, say, in Sydney, and we found 38 in Halifax and 40 in Sydney, we could calculate the individual sample proportions. But if we wanted a single estimate, a pooled estimate, we would take the 38 plus the 40 to give us 78, and then take the two samples, which is 100 and 100, to give us 200. So now we have 78 out of 200, which then gives us 39. So we would have a pool sample estimator of 39%. That's essentially what we're doing. We're taking the two samples that we've obtained from the two populations and we're combining them together. Question is why? Why do we have to do this? Well, let me explain that. If in case 1, we're making the following claim. So we'll say the null hypothesis pi 1 minus pi 2 could be one of three possibilities. It could be greater than or equal to 0, or less than or equal to 0. I'm putting all three of them in 1. So what would happen is that when we're doing the test, we must set the difference to a particular value. So we would essentially set the difference, pi 1 minus pi 2, to be equal to 0 when we're doing the test. That allows us then to set the parameter for the population here, pi 1 minus pi 2. So we need to set it to a specific value. And then we look at the sample data to determine the strength of that sample data. Now, if in the null hypothesis we are saying pi 1 minus pi 2 is equal to 0, essentially we are saying pi 1 is equal to pi 2. Well, that's the only way the difference between them could be 0. There's no difference between them, so which means they must be equal. And so they should be equal to the value pi. Now, under normal circumstances, our z value would look something like this. P bar 1 minus P bar 2, pi 1 minus pi 2, and we would love to be able to put pi 1, 1 minus pi 1 over n1, plus pi 2, 1 minus pi 2 over n2. Well, of course, this is problematic because you cannot be hypothesizing about the difference between pi 1 and pi 2 and at the same time assume that you know what these values are in the denominator. If we knew what those values are right here, if we knew what they are, then we would not be hypothesizing about the difference. We would know exactly what the difference is. The reason why we're hypothesizing because we don't know what those values are. And so all we know is that there's no difference between them. So it could be 0.4 and 0.4, 0.5 and 0.5, 0.25 and 0.25. We're not sure. But we do, according to our formula, we are assuming that there's no difference between them. So if there's no difference between them, and we don't know what they are, our best guess, our best estimate, is to use the sample proportions. Now let's just take a look at the sample proportions and see what we have. So I'm replacing this. So if I'm going to use the sample proportions, I would use p bar 1, 1 minus p bar 1 over n1, p bar 2, 1 minus p bar 2 over n2. But that is problematic as well. Why? Because now we're going to use two sample values to estimate. So for p bar 1 should estimate pi 1 and p bar 2 should estimate pi 2. However, it is very likely that those two values are not the same. The two sample proportions would be different. So how could two different values be estimating the single or the same value, a single value? It's not possible. We cannot use two different values to estimate the same thing. So what we now need to do is to create a single estimate. And we could create that single estimate by removing the subscripts. So that's what we're going to do. So now instead of using p bar 1, p bar 2, we will use p bar, p bar, p bar, p bar. So now we're now going to use the single pooled value to estimate pi over here. Okay? So we want a single value. How do we get this value? That's where the formula comes in. If we know that p bar 1 is x1 over n1 and p bar 2 is x2 over n2, and in case you're wondering what are those, well, x1 will just be the number of observations, favorable observations in sample 1, and x2 favorable observations in sample 2. So in the case of the Coke example I just mentioned, for Halifax, 38 out of 100, so x1 would be 38, and then n1 would be 100. In Sydney, x2 would be 40, and then n2 would be 100. So we get 38% and a 40%. But now we're saying if we want a single estimate p bar, what we should do is to bring those two samples together. We'll add up the observations from sample 1 to the observations from sample 2, and then the two sample sizes, we'll add them together. And then this way, we will get our pool sample proportion. That's how we get that. Now, note something here, that x1 is the same as n1 times p bar 1, and x2 is the same as n2 times p bar 2. Well, if we need to, we could do a variation on this formula right here, the formula for the pool sample proportion. Instead of using x1, now we could use n1 p bar 1, instead of x2, n2 p bar 2 over n1 plus n2. So those two are the same, x1 plus x2, n1 plus n2. All right? What we essentially are telling you is that this term is the same as x1, and this term is the same as x2. And we got that from simply doing some algebra over here. Good. So now that we understand, in this case, when in the null hypothesis we assume that there is no difference between the two proportions, we must now use a pool sample estimate. And that gives us the following test statistic. which we already saw earlier, it gives us the following test statistic. It gives us Z is equal to P bar 1 minus P bar 2 minus pi 1 minus pi 2, which happens to be 0, over P bar 1 minus P bar over N1 plus P bar 1 minus P bar over N2. We could factor out the P bar 1 minus P bar and give ourselves a formula that looks like this. P bar 1 minus P bar 2. We could just get rid of the 0, we don't need to show it. And we would have P bar 1 minus P bar. So I'm factoring that out into 1 over N1, 1 over N2. Okay? That's just another way to write the formula. Either one would be fine, you'll get exactly the same value. So that is case 1. So here are the variations in terms of the hypotheses for testing the difference between two population proportions. And remember again that everywhere you see P, it should be pi, so that should be pi 1 minus pi 2. Okay, so everywhere we see P, remember to replace it with pi. And so in case of a two-tailed test, we would have either that in HO, there's no difference between the two population proportions. There is a difference between the two population proportions. One-tail test, one is a left tail and one is a right tail. And the left tail would be saying that P1 minus P2 is less than or equal to 0. In other words, P1 is smaller than P2. And in the right-tailed test, we're saying P1 is greater than P2. And here we are in the right tail. We know that for a two-tailed test, we split the significance level into 2. So this would give us alpha over 2, alpha over 2. In the case of a single-tailed test, then this is alpha completely, and this is alpha completely. We simply use the table to find the appropriate critical value, and then we conduct our hypothesis tests. Let me examine case 2. Let's take a look at this example which deals with case 1. And case 1, you may recall, is the case where in the null hypothesis, we assume that the difference between the population proportions would be 0. So here's this example. A company has a critical component, a critical component of a handheld hairdryer is the motor heater unit. A company has recently created a new motor heater unit with fewer parts than the current unit. The company has decided to test the samples of old and new units to see which motor heater is more reliable. The null hypothesis states that the new motor heater is no better than the old motor heater. So, in essence, we want to check whether or not one is better than the next. So, in this case, we could assume that the new motor heater is better than the old, which is what is being tested here, a one-tailed test. That's actually being measured perhaps by the number of problems that you have with a particular in a sample. So we have here for the data that 2 samples were taken, both of them of the same size, 250 units were tested, and in the new units we had issues with 55 of them. In the old units we had issues with 75 of them. So 55 and 75. That gives us sample proportions of 22% of the new units had issues and 30% of the old unit had issues. So the question is the new unit better than the old one? So we would frame the hypotheses as follows. If we let pi 1 be the proportion of new units that are defective, and then pi 2 for old units, then we would expect pi 1 minus pi 2 to be less than 0. If the new unit is better, we have fewer issues. Or if we actually took pi 2 minus pi 1, we would expect then the old unit to have more issues. So we could frame old and new, or 1 and 2. I would have used old and new and have this as my hypothesis. HO, I would say pi new minus pi old is greater than or equal to 0. That means that essentially there's no difference between them, or in fact the new one has more issues. HA would be that pi new minus pi old is less than 0. So which means I'm having fewer problems with the newer item, and so my pi new should be smaller than my pi old. We're now given sample data where the sample sizes are 250 each, and then for sample 1, which is for the new unit, we have 55 of the units had issues, and then for the old unit we have 75 of them had issues. So the sample proportions are calculated right here. Okay, sample proportions are calculated right here. Now all we need to do is to figure out what our test statistic is, the decision rule, and then do our computation. Well, the test statistic, because this is case 1, we would use, here's our test statistic we would use. Alright? So that's the test statistic. And notice that we would need our sample, our pool sample proportion, P bar, which you could see under the square root sign right here. P1 minus P2, even though it's in the equation, actually is equal to 0. So keep that in mind. So you could actually remove it, and you can see that right here where we have it set to 0. So that's our test statistic. Our decision rule, this is a one-tailed test, and we're going to test at a 5% significance level. So it means that that one tail, the area is 5%, alpha is 0.05, which means that our Z critical value is negative 1.645. I notice negative because we're on the left side of that 0. It's a left tail test. So now all we need to do is to calculate the value of our test statistic and compare to negative 1.645. When we compute that value, we found it to be negative 2.04, which actually brings us into the rejection region. So since it brings us into the rejection region, we can go ahead and reject the null hypothesis. So this is negative 1.645 as our critical value, and so negative 2.04 would be somewhere in that rejection region. And the p-value associated with that, by definition, is the probability of observing that value or values that are even more extreme. So we could certainly go ahead and find the p-value associated with negative 2.04. But if we're just doing the classical method, we would compare negative 2.04 to negative 1.645, in which case we would reject the null hypothesis. That's our decision in step 5, and our conclusion would be we have sufficient evidence that the new unit is better in the sense that it's more reliable because it seems to have fewer problems. Okay, what kind of error might we commit? Because we are going to reject the null hypothesis, we could commit type 1 error, and the risk of type 1 error is our p-value. So what is our p-value in this case? Our p-value, let's make some space for that. Because this is a left tail test, so our p-value will be the probability of Z being less than or equal to negative 2.04, which would be 0.5 minus the area associated with negative 2.04. So let's look that up and see what that turns out to be. The area associated with negative 2.04 turns out to be, when I look at my table here, 0.4793. So our p-value is 0.5 minus 0.4793, which gives us 0.0207, or 2.07%. Well, if you compare this to alpha, it's definitely less than alpha, which is 0.05. And therefore, we would have rejected the null hypothesis on the basis of just the p-value alone. So having said that, we could then come to the same conclusion. So since the p-value is less than 5%, we will reject the null hypothesis and conclude we have sufficient evidence that the new unit has fewer issues, or the new unit is more reliable than the old one. All right? So that would give us our conclusion. So decision would be, so our decision would be to reject HO. Our conclusion, we have sufficient evidence the new unit is more reliable. Okay, can we be wrong? Yes, we could be wrong. We have the risk of type 1 error. And what's that risk of type 1 error? Is the p-value, which is 2.07%, which is not a very high risk associated with committing type 1 error. And that is how we would work this problem out. Okay? So with case 2, what's the difference? Well, we're going to say now in the null hypothesis, pi 1 minus pi 2 is equal to some value. But it so happens that that value is a non-zero value. It's not 0. Pi 1 minus pi 2 is not equal to 0. Sorry, but it's not equal to v, that value. So I could have hypotheses like this, testing whether or not the difference between two proportions is 5% or not 5%. So pi 1 minus pi 2 is not 5%. The difference is not 5% versus pi 1 minus pi 2, the difference is 5%. So I'll assume this in the null hypothesis. So as you notice, this would be my value v, but v is a non-zero value. This is our value v as well, same 0.05. So what do we do in this case when we have a value here that is non-zero? In this case, pi 1 is not equal to pi 2. We're hypothesizing there's a difference between them of 5%, but pi 1 is not equal to pi 2. So what can we do in this case? We would simply have to use the sample proportions to estimate them. That's our best guess at this point in time. So we use that. And our test statistic now would look like this. Z is equal to p bar 1 minus p bar 2, pi 1 minus pi 2 divided by p bar 1, 1 minus p bar 1 over n1, p bar 2, 1 minus p bar 2 over n2. So that is what it would look like now. And so notice the difference is that I'm not using a pooled sample estimator, p-bar. I'm just using the actual sample proportions that I obtained. And then the rest of the steps are pretty similar to what we've done in the past. Keep in mind that this is a normal distribution, so we tend to float in and out of the t value and then the z value. So just keep in mind which situation that we're dealing with. Whenever we're dealing with proportions, we always use z. We do the analysis as long as the normal approximation to the binomial set of conditions are actually satisfied. So to finalize things, or to summarize things, we could say in case 1, if that's what we're dealing with, HO pi 1 minus pi 2 is equal to 0, and our test statistic is equal to P bar 1 minus P bar 2 minus pi 1 minus pi 2, which turns out to be 0, over P bar 1 minus P bar 1 over N1, 1 over N2, but we must bracket that. So that's case 1. Case 2, where in HO, pi 1 minus pi 2 is equal to a value that is not equal to 0. Then in this case, our test statistic is P bar 1 minus P bar 2 minus that value, which we get from the null hypothesis. That's pi 1 minus pi 2, that's the value, divided by P bar 1, 1 minus P bar 1 over N1 plus P bar 2, 1 minus P bar 2 over N2. Okay? And those are the two cases that we got to deal with. I should just mention something to you here which might be useful. Whenever we're doing in our alternate hypothesis a test like this, for example, pi 1 minus pi 2 is not equal to 0, we could actually solve this problem as well by getting a confidence interval. The equivalent of this test is a confidence interval. That's the same for actually all the hypotheses that are two-tailed tests, where you would use P bar 1 minus P bar 2 plus or minus Z, and if we just find a confidence interval, interestingly enough, we simply use the sample values that we have. P bar 1, 1 minus P bar 1 over N1 plus P bar 2, 1 minus P bar 2 over N2. Notice we don't use a pool sample proportion in this case because we have not said anything about the difference between P1 and P2. We simply go in ahead and finding a confidence interval for that difference. But whenever we're testing a hypothesis where there is a difference, that is a two-tailed test, our two-tailed test can be addressed also by a confidence interval. Good. So we will review those concepts and make sure that we understand how to go ahead and calculate or do a z-test for the difference between two population proportions.